Welcome to this section of the Physics Tutor where we're going to talk about something very, very important, and that is the concept of kinetic energy, and also we're going to talk about something called the WorkEnergy Theorem. And in my opinion, this is when physics really starts to get interesting, when you start talking about energy, because you can look around the world, roller coasters and all kinds of cool things, and you can see how energy and work are really interplay with one another. So pay attention to this stuff. It's very core material. Everybody has their definition of what the word energy means. Think about it for yourself. You can pause the video. What do you think energy is? Most people think of energy as maybe a lightning bolt or, I don't know, somebody that's moving pretty quickly or something like that has energy, some vague notion. But when you really think about it, is energy electricity? What is energy? Well, it's a tough nut to crack, really. But in physics, in classical motion, which is what we're studying here, energy has a very specific definition, just like work had a very specific definition. So let's go ahead and talk about that now. Very simply, we have this thing called kinetic energy, and I'm going to abbreviate that KE, okay? Kinetic energy. And it's a very simple equation, okay? And it's equal to 1/2 times m, which is the mass of the object, times the velocity squared, okay? So very simply, if you have some baseball or something that has a certain mass, okay, that's the mass here, and you throw that baseball and it has a certain velocity, then all you do is you take the velocity, square it, multiply by the mass, multiply by 1/2, you have what we call kinetic energy. Why does it have a 1/2 in there? I don't know. It's the way the universe works, okay? Why is it m times v squared, not v cubed? Why is it m instead of m squared? I don't know the answer to these questions, but you can look at objects in the world and you can calculate the energy, and you'll find that it's a very accurate representation of what the energy is, and it's represented by this equation. It's called kinetic energy because it's just like coefficient of kinetic friction. It implies the energy of motion, which will be different from other kinds of energy that we're going to study a little bit later on, okay? So basically you can regard this as the equation as the energy something possesses when it moves. So a safe is going to have a larger mass than a ping pong ball, right? So even though both of them move at the same velocity, the safe is going to have a higher kinetic energy than the ping pong ball will, which kind of makes sense, okay? So the kinetic energy has units of, and this is going to probably blow your mind, joules, okay? Which is, if you remember, the same exact unit that work had, okay? So you might say, well, aren't they different? Why do they have the same units? Okay, you're going to find out here in just a minute that work and energy are similar, okay? And they have the same units. So you'll find that the work has a unit of joule, the kinetic energy has a unit of joules, and in a little bit we're going to get to potential energy, and it also has a unit of joules, okay? So there's lots of different things with the same unit, and I'm going to try to explain to you why they're different. In order to do that, let's take a little thought experiment. I'm going to do this in a different color, just for kicks, okay? So let's say you have some box right here, okay? And let's say you push on this box with some force F, just like we had in the previous section there, okay? Sometime later, the box is obviously going to move over here to the right, okay? And again, you're still applying that force, even though it's moved. You're applying that force throughout the whole thing. Now, initially, the box was at rest, so the velocity was 0, and then whenever you move it over here, it's going to eventually have some final velocity greater than 0. All this is saying is that initially the box was at rest, I push it, and then it has some velocity not equal to 0. This could be 10 meters per second or something. And also, obviously you're moving it through some distance d. Okay? Okay, so the big picture is, and this part of it's really the same from the previous section, I'm trying to draw these concepts together so you understand the big picture. When you push on an object that has a mass, which by the way I didn't put it in here, but this has a mass, and this has a mass obviously, and you push this object through a distance d, you do work on the object, okay, because you have to get it to move, so you're doing work on the object, and we already talked about that, okay? So the work done on the object was just simply F times d, force times distance. I'm not introducing anything new here. I'm sort of reviewing the old concepts here, okay? Or if the force was not in the direction of the motion like it is here, then it would just be F cosine theta times d, where theta is the angle of the force. We all talked about this in the last section, so there's nothing new here. But when you do this, even though you can calculate the work, you also know that something else is going on. Well, the block is moving, and not only is it moving, it's accelerating, okay? So the object has an acceleration now, okay? And how does it accelerate? Think back to the previous sections. The force is equal to the mass times the acceleration. So if I know the force that I'm pushing on this block, and I know the mass of this block, this will predict what acceleration I will have. And this is all starting to make sense, because when you push on the block, it has an acceleration, which then speeds up its velocity, and that's why the velocity is now non-zero, okay? So as a result of the object acquiring an acceleration, the final velocity, which is this final velocity here, is obviously going to be greater than the initial velocity. All I'm saying in all of these little steps here are some really gee whiz, gosh, this is really stupid type of concepts, okay? This is very simple. You're pushing a block, you're doing work on the block, and the block speeds up. This is all this is saying. Velocity, the final velocity is greater than the initial velocity. The velocity the box speeds up, okay? Now, because of our definition of the kinetic energy, if the final velocity, which is this, is greater than the initial velocity, then that means that the final kinetic energy of the box has to be greater than the initial kinetic energy of the box. Now we're starting to get into the new material. But again, it really isn't saying anything too absurd or too hard to swallow. Okay, if the box speeds up and the mass is the same, well then of course, since we've defined our kinetic energy this way, the final kinetic energy over here will be greater than the initial kinetic energy here, because the box wasn't even moving when we started, okay? So that makes sense. So when we do all this, the kinetic energy increases. Again, nothing too earth-shattering. You push a box, the kinetic energy increases. It kind of makes sense, okay? Now here's where I start to tie everything together. The work you do on the box, okay, goes, and I'm writing this out for a very specific reason, into increasing the kinetic energy. Okay, now that's a very important statement, and it's very easy to look at that and just say, okay, well that makes sense, and move on, okay? It's very important. When you push the box, you're doing work on the box, okay? And that was governed by this equation, a totally separate equation than this kinetic energy. But it turns out that because you're pushing it and the object speeds up, and because we've defined kinetic energy this way, the kinetic energy increases, okay? And it turns out that every joule that you add to the system in work increases the kinetic energy by 1 joule, okay? I'm going to point this out very explicitly here. The unit of work is joules, and the unit of kinetic energy is also joules. That's why it's important that the two units are the same, and that's exactly why the system, the smart guys that came up with all this stuff hundreds of years ago, defined everything this way. When you define work in terms of force times distance and define the unit in joules, and you define the kinetic energy in terms of this, in terms of joules, everything makes sense. You're starting to see some of the elegance of physics here, okay? And it may not make 100% sense yet, but just think about it. You push a box, we can calculate the work done on the box, okay? So if there's no losses in the system, no friction, no anything, air turbulence, nothing like that, a very pure physical system, which is what we're always going to talk about in these classes, okay? Every single joule that I put into the system as work done on the system, in this case it's a box, okay? Every single joule that I put in, that joule has to go somewhere, okay? It can't just be lost. It can't just float off into space. That joule goes into increasing the kinetic energy of this box, okay? Very, very important. So if you know the work done on the box, then you sort of already know what the kinetic energy of the box is, or at least you know how much the kinetic energy increased. Because every single joule going into the box in work, in the form of work done on the box, must increase its energy in some way. In this case, we're increasing the kinetic energy. Okay, and I'll give you a preview of the next section when we talk about potential energy too. In this case, if I have this marker, I can move it up. I put some work into raising this guy. Well, in this case, I'm increasing the potential energy of the system. That's just a preview of the next section. In this case, we're increasing the kinetic energy, the energy of motion. In this case, I'm increasing its potential energy because I'm moving it higher from the Earth. And the higher you are from the Earth, the more potential it has to do work, okay? So that's just a preview. But for now, we want to talk about the kinetic energy and the work. Okay, that's all very, very important stuff leading up to a pretty important theorem that we're going to talk about right now, and that's called the WorkEnergy Theorem. And the good news is I've already really taught you what that theorem is, or what it says, without even writing a real tough-looking equation on the board. So now I'm going to write a little equation on the board, and we're going to talk about why it makes sense. Okay, you have something called the WorkEnergy Theorem. In equation form, all it means is the following. The net work done on a system, in the other case it was a box, has got to equal, let me just write this down, the final kinetic energy minus the initial kinetic energy, which is equal to the change, remember delta means change, in kinetic energy. This says nothing more than what I've already told you in words. You do work on a system, in this case it's a box, you do some work on that system. That work must go somewhere. It goes into increasing or changing your kinetic energy. And the change is governed by the final kinetic energy minus the initial kinetic energy. So in the other case, the initial kinetic energy was 0 because the box was stationary. So every joule I put in must have increased its final kinetic energy because its velocity increased, okay? So if I were going to write this out a little bit more explicitly, I would say the net work done on a system would be 1/2 mvf squared. That's just the final kinetic energy of the system, minus 1/2 mvi squared, which is just the initial kinetic energy of the system. I've really said nothing new. I'm just writing it out in terms of the kinetic energy. So this is called the WorkEnergy Theorem, and it says exactly what I've already told you. Every joule you put in has to go somewhere, and since now we're talking about kinetic energy, you're pushing things, that energy, the work that you put in the system, in this case, went into increasing the kinetic energy. So with that, let's use the WorkEnergy Theorem and let's solve a couple problems. Okay, problem on your screen says somebody's throwing a baseball and they're throwing it at a speed of 40 meters per second at an angle of 30 degrees. What is its kinetic energy at the highest point of the motion? Okay, so you have a guy, and this is X and Y, and he's throwing some baseball, and the baseball obviously is going to go up and it's going to come down, okay? Kind of like we've had a lot of problems. Throwing it at an angle of 30 degrees, okay? And the initial velocity is 40 meters per second. That's the velocity of the ball going up, okay? Also, the baseball itself has a mass of 0.15 kilograms. Okay, so that's the correct units. We have meters per second and we have kilograms, so far we're okay. Question is, what is the kinetic energy of the ball at its highest point, which would be here, okay? Highest point here. So I should ask you, what you need to do, obviously, the formula for kinetic energy, which is what the problem's trying to ask you about, is 1/2 mv squared. Now you can't use 40 meters per second here because the problem doesn't ask you what's the kinetic energy here. It asks you what is the kinetic energy at the highest point. And so you have to make sure you're using the right velocity here. Obviously, as you throw the ball up, the ball is going to go up and the ball is going to go down. So at this point, the vertical motion, the up and down motion, is 0, right? At the highest point. The horizontal motion is going to be the only motion that you have up here, and so the horizontal velocity is going to be the velocity that you're interested in right here. Okay, so let's do that. Let's figure out what the horizontal velocity is along here, okay? How would we do that? The x component of the velocity here is going to be what? You have an angle, you have a vector here. How do you do that? You have to use the cosine to get the x component. So it's going to be 40 times the cosine of 30 degrees, okay? That's going to be the x component of the velocity. And then if you put this in a calculator, cosine 30 times 40, you're going to get 34.6 meters per second. Now I want to do a little bit of a review here on projectile motion we've already talked about. The gravity only acts in the y direction, okay? So when I calculate this x value, that means that I throw it up at an angle of 30 degrees, but the x component, the velocity component along the horizontal direction is 34.6 meters per second, and it does not change, okay? Even though the ball goes up and even though the ball goes down, we're using the power of vectors here. I'm decomposing that vertical motion, which I don't care about. I'm interested in the x component right now, okay? Which came out to 34.6. Throughout the motion, the x component is not acted upon by gravity because gravity does not act in that direction. So that 34.6 is constant. If you were to look at it from here to here, the horizontal component of the velocity would stay constant. It's only the y component that's being influenced by gravity, and that's why the y component changes. The y component is big, and then it goes up, and it gets to 0, and then it gets large again as it comes back down, okay? The x component is 34.6. So at the apex, which is just the highest point here, is what they're talking about, the y component is simply 0. There is no y component because whenever you throw the ball and it gets to the top, the y component goes to 0 before it comes back down. Therefore, the velocity, the total velocity of the baseball up here has to be 34.6 meters per second. The x component is the same, the y component is 0, so the velocity that we're going to be interested in at the apex is 34.6. And so then the kinetic energy is simply 1/2 mv squared. So I'm going to have 1/2, the mass is 0.15, okay? And then the velocity is going to be 34.6 meters per second, and I'm going to square that. So then the kinetic energy, when you multiply 1/2 times this squared, is just going to come out to 89.8. And what are the units of energy? Joules, okay? 89 joules. What does 89 joules mean? I don't know. It's the energy of a baseball here when you throw it like that. But I wanted to make sure that you understand that you gotta look at the problem here and figure out, okay, at the apex, I need to find the velocity of the ball. There is no y velocity. The only x velocity here is the one I can calculate. So that's the one that I need to go ahead and use. I'm going to go ahead and work another problem here. And these problems are, you're going to hit some critical point at which all this stuff starts to make sense. And I'm hitting you with a lot of different topics, and that's why people have such a hard time with physics, because there's tons of definitions, and most of them are kind of counterintuitive, and then you get to a bunch of problems and they just don't make sense. I'm really hoping that as we work a lot of problems here, some of this stuff will start to make sense. So the next problem is you have a 0.6 kilogram particle, and it's moving at 2 meters per second at point A. And at point B, it has a kinetic energy of 7.5 joules. Questions. What is the kinetic energy A? What is the speed at point B? And then we'll just go on from there. So the particle, which is a baseball or something, is right here at point A. Okay. Here, let's do this a little bit differently. It's at point A here. The mass is 0.6 kilograms. Obviously, that's not going to change. Okay. The velocity, I know, at this point, at point A, is 2 meters per second, okay? And then also, at some point later, I mean, who knows, at point B, the only thing I really know is that the kinetic energy over here is 7.5 joules, okay? First question says, what is the kinetic energy at point A? So the kinetic energy at point A, I'm going to put a subscript saying at point A, is just going to be 1/2 mv squared. And we know the mass, we know the velocity, so this is super simple. 1/2 times 0.6 times v squared, okay? And then when you do that, when you plug all this in, then you're going to get an answer that's going to be 1.2 joules. So that was the first part of the problem. What's the kinetic energy at point A? 1.2 joules, okay? Second point says, it's wanting to ask us at the second point, what is the speed at point B? Now here, we know the kinetic energy, and it's asking us to calculate the speed. So again, the kinetic energy at point B is also 1/2 mv squared, the velocity being the velocity over here at point B. Okay, so the kinetic energy, I know, is 7.5 equals 1/2. The mass, I also know, 0.6 kilograms. That obviously isn't going to change. The velocity is what I'm trying to find, okay? The velocity at point B. So if you take 7.5, you divide by 1/2, you divide by 0.6, then what you will have is the velocity at b squared is going to be equal to roughly 25. So when you take the square root of that, the velocity will be 5 meters per second. Okay, so we calculated the kinetic energy at A, we calculated the velocity at B. The third part of the problem is really the most interesting part. It says, what is the total work done on the particle as it moves from point A to point B? Now here's where things get interesting, because it's asking you for the work done on the particle. The particle is here, particle moves here, but I don't tell you the force pushed that the particle is being pushed with, and I definitely didn't tell you the distance the particle moved with. So this is kind of one of those things where you could look at it and say, well, how do I calculate that? Because we all know that work is force times distance, right? And I didn't give you the force and I didn't give you the distance, but I did give you this really interesting, cool theorem, the WorkEnergy Theorem, that basically says every bit of work you do on the system, in this case the system is a particle, a baseball or something, has to go into increasing the kinetic energy, okay? Which is, so it's equal to the change in kinetic energy, final kinetic energy minus initial kinetic energy. I know the initial kinetic energy because I just calculated it right here. I know the final kinetic energy because that's what they ended up giving me in the problem, okay? So the work done, according to the WorkEnergy Theorem, is the change in kinetic energy, which is the final kinetic energy minus the initial kinetic energy. That's what I'm interested in here, okay? So the final kinetic energy was 7.5. The initial kinetic energy I've already calculated here is 1.2, okay? And then when you do that subtraction, you'll find that the answer is 6.3 joules. And notice we calculated that without knowing the force acting on the ball and without knowing the distance through which the ball moved. We calculated that purely based on knowing the kinetic energy. Now this is the kind of thing you could do in a lab. If you happen to know the velocity of some particle somewhere and you happen to know the velocity of the particle somewhere else, you can simply calculate the velocity. You can calculate the energies involved. You could subtract them, and then you know from that you would know the work done. And how could you measure the velocities? Well, you could use like a radar gun a police officer had. You could go and shoot a baseball and say, well, that's going 50 miles an hour. Convert that to meters per second, and you could use it. It's the kind of thing you can really use if any of you guys are interested in being a physicist that works in a lab or something like that. Okay, I'm going to work one more problem dealing with work and energy before moving on. Work and kinetic energy, I should say. We haven't even talked about the topic of potential energy, but I'll promise you when we get there, that's not going to be very complicated either. Okay. Next problem says you have a bowling ball at 7 kilograms, moves at a speed of 3 meters per second. How fast must a ping pong go? And it gives you the ping pong mass here, which is 2.45 grams. How fast must the ping pong ball go so that the two balls have the same kinetic energy? So let's draw a picture. You have a giant bowling ball. The mass is 7 kilograms. Okay, and that guy is moving at a velocity of 3 meters per second. You also have a much smaller ping pong ball, the mass of which was given as 2.45 grams. Okay, the velocity is what we do not know. So what we want to figure out is, okay, this guy obviously has some kinetic energy associated with it. It's got a mass and it's got a velocity. You have a ping pong ball here. I know the mass. I want to know how fast does this ping pong have to travel in order to have the same kinetic energy as this one, okay, as this bowling ball, which is obviously much heavier. So this ping pong ball, just from common sense, is going to have to move awfully fast in order to have the same energy as this bowling ball that's traveling at a slower speed. First thing I want you to see right away, they give you kilograms here, which is a good unit, the unit that we always deal with. Meters per second here, which is fine. Here, they try to trick you, or I tried to trick you, with a mass in grams, okay? So right away, you're gonna have some problems because eventually you're gonna have to convert that to kilograms if you're gonna use the formula that we have, 1/2 mv squared. You have to have the consistent units. But before we get there, let's calculate the kinetic energy of the bowling ball. Okay? And that's going to be 1/2 mv squared. Okay? So that's going to equal 1/2, mass was 7, velocity was 3 squared. And when I take these three things and multiply them, you have 3 squared, which is 9, times 7, times 1/2, then you will get 31.5 joules. That is the kinetic energy of this ball because it is moving, okay? Now what you really want to do is you're going to also set up another equation over here. You're going to have the kinetic energy of the ping pong ball, okay? And that's going to equal 1/2 times the mass of the ping pong ball times the velocity of the ping pong ball, which is what we're trying to calculate. But the mass here isn't going to work because the mass, to use these equations, you have to have the correct unit, and the correct unit here is kilograms. You can't really operate in grams. So what we need to do is convert 2.45 grams to kilograms. And if you can't do that in your head, you could say 1 kilogram is 1,000 grams. Grams cancel. I'm left with kilograms on the top. So you have 2.45 divided by 1,000, and you will get 0.00245 kilograms. It makes sense that it's a small number because the mass is a ping pong ball after all. I mean, it's a pretty small little ball. Okay, the question is, how fast does this guy have to go to have the same kinetic energy as the bowling ball? So what we want to find is what value of V do we have to put in here such that the kinetic energy is equal to this kinetic energy over here. So I'm going to set this up by saying 31.5, which I'm going to say is the kinetic energy of the ping pong ball now, is equal to 1/2, okay, times the mass of the ping pong ball, which we calculated in the correct units, 0.00245, times the velocity of the ping pong ball squared. Okay? So really what you want to do is you want to take this and multiply it by this, which you can do in your calculator. You take 31.5 divided by that value to get V squared by itself, and you'll see that V squared is going to be equal to 25714.3. Pretty big number. In order to find the velocity, you have to take the square root of this, which will be 160 meters per second. So you can see right away, you had a bowling ball traveling at 3 meters per second. In order to have the same kinetic energy, this ping pong ball needs to be traveling a whole lot faster at 160 meters per second, and that makes a whole lot of sense. Since a ping pong ball doesn't have as much mass as a bowling ball, you have to give it a lot more speed in order for it to have the same kinetic energy, and that's exactly what we've shown here.